So we're going to wrap up this Lecture 4 series with this last chunk C here. This is going to be probably the briefest of the 3 lectures. Again, this is the first half of Chapter 6 from your textbook, and we already spoke about enzyme kinetics and thermodynamics, making the universe happy with negative delta G's and energy release. In the last chunk, we talked about determining the rate of catalyzed reactions, and we also talked about order of reactions, 0, first, and second order. And here we'll spend a few slides talking about enzymes that bind to substrate, again, substrate being a synonym for reactants, and how enzyme-substrate binding occurs, what it achieves, and why it's important. So let's get right into it, enzyme-substrate binding. What enzymes are really doing here is working on reactants. Like that bread machine takes the raw ingredients of bread, flour, water, salt, and eggs, and changes it into transition state, so too will enzymes work on substrate, changing them into transition state. So if enzymes are going to do that and work on reactants, then of course the very first thing they need to do is physically interact with and bind to those reactants, which we will then call substrate. This results in what we refer to as the enzyme-substrate complex, a single complex made up of the enzyme and the substrate bound to it. Once the enzyme-substrate complex forms, that bread machine gets to work. Now, the enzyme will start physically pulling, stretching, ripping, hammering, pummeling, and squeezing that substrate molecule or molecules until they become transition state. This is the energy or work that would have been needed from the universe, but now the enzyme is doing that work instead. This is how the enzyme lowers the energy of activation. It is doing some of the work that the universe would have otherwise had to invest into the reaction. Once the enzyme does all of that work and distorts the substrate into transition state, remember the rest takes care of itself, and energetically transition state will collapse into product all on its own. That recoups the energy that the enzyme put in, and also releases the free energy that is the difference or the balance of this reaction as we go to product. This is the delta G energy that's released to the universe. We can represent this overall process in this way. The enzyme on its own somehow is floating in the same environment as the substrate on their own. The two collide together and form the enzyme-substrate complex. This is where the enzyme gets to work and finally makes transition state, and then transition state automatically collapses into product. Remember, we spoke briefly about enzymes having specificity. This is the idea that enzymes bind to and work on one thing and one thing only. What enzymes bind to and work on is substrate. So this enzyme in this example is evolved to bind to this substrate molecule. It binds to it. It pulls on it and works on it. It forms that substrate into transition state. Transition state collapses into product, and the enzyme very quickly says, "Product? What the heck is this?" and lets go right away. Because the enzyme is evolved to bind to substrate, and product obviously is not substrate. So once product is formed, the enzyme instantly and spontaneously lets go because the enzyme is not built to bind to product. Where that substrate is binding specifically in the enzyme is referred to as the active site. The catalytic site we referred to a few lectures ago. This is called the active site of the enzyme. It's where the work of the enzyme occurs. This is a cleft or crevice within the enzyme itself that holds the proper substrate in just the right orientation so that the catalysis can occur. Remember the idea of specificity. Nothing else can bind to that active site but the proper substrate, and this allows the enzyme to do its one job and its one job only. All of the chemistry of that reaction, all of the chemistry catalyzed by the enzyme, is occurring right there in that active site. Usually. There are some rare exceptions, but that's largely true. The substrate molecule is bound to that active site and bound to the enzyme in general by making numerous non-covalent contacts with the side chains and the backbone of the enzyme molecule or protein itself. Remember, the enzyme is a protein, so it's made up of amino acids in a chain. The enzyme is folded into some tertiary or quaternary shape based on the sequence of those amino acids, and so the substrate molecule is making contacts with the side chains of those amino acids. All of these contacts taken together gives the specificity of enzyme-substrate binding. And it is these same contacts that allow the enzyme to grab hold of that substrate and twist it and pull it and manipulate it, making that substrate become transition state. For a long time, enzyme-substrate binding was referred to as a lock and key model. The idea here was that the active site of the enzyme had some type of complementary or mirror image structure that perfectly matched or complemented the shape of the substrate. So as this example shows here, the substrate molecule in 3 dimensions fit perfectly into the active site, and that's where we would have specificity. It's been shown, however, that this model is inaccurate. This is not exactly how it works, and instead, we now have adopted in biochemistry what we refer to as the induced fit model, and the induced fit model is much more accurate. The induced fit molecule states that, well, yeah, there's some kind of mirror imagery complementation occurring here, where the active site in some ways matches the shape of the substrate, and we can see hints of that here. This general shape of the active site somewhat mimics and matches the shape of the substrate here, but it's not a perfect match. So substrate can fit into the active site, of course, so that the enzyme-substrate complex can form. The active site is flexible and it can kind of mold around the substrate. But additionally, substrate binding induces conformational changes, like that person fainting at Inauguration Day. And so the whole protein, the whole enzyme now, is kind of changing its shape to mold around and accommodate substrate binding. This is needed because enzyme-substrate complex forming, in other words, substrate binding to the enzyme, has to be thermodynamically favorable. It can't require too much energy, otherwise it would never happen. But the induced fit model predicts another important point. Enzyme doesn't like binding substrate above and beyond anything else. Said another way, substrate is not enzyme's most preferential thing to bind to. It wouldn't be good for the enzyme to fit perfectly with substrate. The lock and key model predicts just that, a perfect fit. Let me ask you this. If you found your perfect fit, would you ever mold that perfect fit into something else? Of course not. An enzyme would do the same. If enzyme and substrate bound perfectly, they would happily stay bound together and nothing would ever happen. What the induced model predicts is that enzyme finds substrate and says, you know, this kind of matches what I like. I'll bind to this substrate molecule. But then it does what all of us do in a relationship and say, this is a pretty good partner to bind to, but I can make them even better. I'm going to change this person to give them a better sense of humor. I'm going to change this person to make them a better dresser. I'm going to change this person to make them a better conversationalist. And enzyme does the same exact thing. Enzyme binds to a near-perfect fit in substrate, but then enzyme gets to work. And it distorts that substrate into making it something it likes to bind to even better. Got ahead of myself here. So what we're saying here is that the enzyme and substrate bind, but they don't bind too well, because what the enzyme really wants to do is bind to transition state. Transition state is the enzyme's perfect match. If enzyme and substrate bound perfectly to each other, they would be so energetically happy that they would never unbind again. So enzyme binds to substrate and likes that, but then enzyme gets to work and makes the transition state. In fact, enzyme's best partner is transition state. That's what enzymes like to bind to best. So here's how it works for enzymes. Enzymes find a near-perfect match. Ooh, here's something that's very close to what I would love to bind to, substrate. And I will bind to substrate. But substrate is not perfect for me. I want substrate to be even better. So I'm going to pull and twist and distort and stretch substrate until it becomes the very thing I want to bind to best. Transition state. And for a split nanosecond, it's a perfect union. Enzyme has what it always wanted. Its perfect binding partner, transition state. But then what happens? Transition state collapses into product. And enzyme says, ugh, product? What is this? And it lets go. And then enzyme is lonely. And it floats around until it finds another near-perfect match, a new substrate molecule. And it says, I like this substrate, but I can make it even better. And it twists and distorts and pummels and stretches until that substrate becomes transition state. And enzyme says, finally, my perfect match, exactly what I meant to bind to. And then transition state collapses into product, and enzyme says, oh my God, what is this? And it lets go. And enzyme continues repeating that process over and over and over again. The plus side for us is that the enzyme is always catalyzing biochemical reactions, speeding the conversion of reactant into product. The downside for the enzyme is every single time that enzyme finds its Mr. Right, it collapses into Mr. Wrong. So it's a very, very sad life for enzymes. And that's what we say here. So the process repeats again and again. Enzyme binds to substrate. Enzyme works on that substrate on behalf of the universe, lowering the energy of activation, that is, lowering the energy the universe needs to put into the reaction by the enzyme working so hard to make transition state itself. The enzyme is eager to do this work because the enzyme thinks it's making Mr. Right. Once that Mr. Right is made and the transition state forms, it's too energetically unstable, and it automatically and rapidly collapses into product all on its own. Enzyme then lets go of that product because it's not meant to bind to product, and the process repeats. The reason why transition state collapses into product is because so much energy is trapped in transition state. It's a high energy, high maintenance molecule, and the universe despises high maintenance, high energy molecules because the universe wants that energy released as heat. And so the transition state exists extremely briefly, and I mean fractions upon fractions of seconds. We have yet biochemically to capture the true physical representation of transition state. It is so briefly lived. Once product is formed, it's let go by the enzyme because it fits so poorly into the active site, and the process repeats again. So this is the life cycle, or the general reaction cycle, of an enzymatically catalyzed reaction. Enzyme and substrate are independent and free-floating. They bump into each other, and they bind favorably. Favorable binding means that energy was not needed. But then energy is inputted into the system. The enzyme works on that substrate, making it its ideal partner, transition state. But that transition state is harboring so much energy, and the universe simply cannot have that. And so this high energy, high maintenance molecule of the transition state automatically and instantly collapses into product, and enzyme lets product go just as instantly because product does not fit well into the active site. Free enzyme then recycles to repeat the process by finding a brand new substrate molecule as well. Different enzymes achieve the specifics of catalysis in different ways, but everything we've said here in the generalities of how enzymes speed the rate of reactions is true for every single enzyme. We'll talk in the next lecture about a specific example of how enzymes make transition state, just for one enzyme to give you a sense of the true details of the catalysis. But everything we're talking about here in this lecture series is in generality, and it's true for all enzymes you can encounter. So to summarize this last chunk, we started by talking about two models to explain enzyme-substrate binding in general: the lock and key model, which is flawed and a little too specific, and the induced fit model, which better captures what is going on. In the induced fit model, active sites will mold or conform to the shape of the substrate. The active site fits substrate, but it doesn't fit it quite well. Instead, once substrate binds, the enzyme gets to work creating transition state. And once transition state forms, then we can make product. I hope you've enjoyed this lecture series. I hope you have found it somewhat interesting. We will move on to some specific enzyme kinetics and speak a bit more detailed about the thermodynamics of enzymatic reactions as we continue on in Unit 1. As always, thank you so much for watching.